This is what I've come to call the have-need chart. So when trying to work through these z-score and area under the curve sort of problems, there are steps that are going either way depending on the problem. So when the values don't fall exactly at whole z-score numbers, like 1, 2, -1, 3, or whatever, and you got to sort of start figuring out the area that for values that are like 1.2 z-score. The process goes something like this: if what I have is the raw score, but what I need is the area under the curve or under the distribution, the steps look like I'm going to take my raw score, I'm going to convert it to a z-score first using this equation, and then I'm going to go to a table, depending on which version, it's either E10 or D10, but it's the z-score table that there's a link for on the class website, if you look there. So you're going to go to the E10 table, which is the Z table, and you're going to start with the Z column. You're going to look up the Z-score, and then you're going to figure out the area that you need under the distribution. Now, other problems will give you the area, and I want to know what Z-score corresponds to that area. So what you have is the area under the curve, but what you need is the raw score, so you're going to go the other direction. You're going to start off with table E10, but this time you're not going to start with the z-score. You're going to start with something like the mean to z column or something like that. You're going to start with the actual probability column. Look up that area in that column to find what z-score corresponds to that area, and then convert the z-score to a raw score using this equation, which is again just this equation rearranged. So we're going to convert the z-score back to a raw score using this. So if I have a raw score, I'm going to go through this process to get an area under the curve. If I have the area and I need a raw score, I'm going to go through this process and go backwards. This is what table E10 looks like, and again, it could be called D10 if you have a different version out there. But the one I think that is on the class website is either labeled E10 or D10. I don't remember. I think it's E10. But I would definitely get used to using that one. That's the one that you'll be provided with, for exams and stuff. The one I recommend using, so you get used to using the same one, because different books, different approaches will do it differently. And if you start switching up in the middle of trying to do a test, it might screw you up. So what it does is it gives you a z-score, like here's a z-score of 0.46. And that gives you 3 values. The value from, what's the area from the mean, from the center, to that value is the first column, mean to z. So it's going to tell you the area between the value of 0, mean, and the value that you're looking for in z. Then you got the larger portion and the smaller portion. Those will always add up to 1. So if we take 0.6554, add 0.3446, you'll get 1. The reason why, it's just talking about taking the distribution, like here's z. If z is over here on the right-hand side, it's a positive number. The smaller portion is going to be the portion that's above it. The reason why it's smaller is because it's smaller than 0.5. Again, the only place where it doesn't apply is for the very first z-score. A z-score of 0 means you're at the mean. So the area between the mean and the mean is 0. The larger portion is 50, the smaller portion is 50. It's the only place where the smaller and larger portions are actually the same size, because it's right exactly in the middle. Everywhere else, as you go positive, you go above the mean, the larger portion is going to be to the left, and the smaller portion is going to be to the right. Okay? Now, I'll talk about it in a second, but if you're talking about negative z-scores, everything sort of flips around, and we'll talk about how to figure that out. But let's just go with this for a second. So you have a positive z-score, like for 0.5. The area from the mean to z is 19% roughly, 19.15%. The area between the larger portion, it's going to be from 0.5 to the left. It's going to be roughly 69.15% or 0.6915 as a proportion. And then the smaller area is going to be the area above 0.5 is going to be this 0.3085 there. And again, these should add up. And that's why it's really important that you draw out, even just really rough, sketch out the distribution, where the point is you're looking for, and then which side, the area you're trying to find, so you can actually know if you're looking for the larger portion, the smaller portion, or even the mean to z. So smaller versus larger portion, again, it's just for all positive z's, the ones on the right, the larger portion is going to be everything to the left of the curve. The smaller portion is going to be everything to the right of the point on the curve. Okay. The area from the mean to z, again, is just that. It's just, if you look at the area from 0 to a standard deviation of 1, it tells you it'll be 0.3413, which is why in the rough estimate chart I said it's about 34%. Right, 0.3413 is roughly 34%, and that's the area from the mean to z. It also means if you go from the mean to -1, it's the same number, the same area. Okay. And sometimes you hear things like area beyond z, and usually beyond is talking about going more extreme. So it can be tricky depending on where you're reading it. If you're on the positive z-score side and saying, talking about the area, you have like a z-score of 2 point something, and saying the area beyond, it's talking about going more extreme, the area beyond that number. But if you're on the other side, -2.16, the area beyond would be that way. So sometimes the language that you'll see used to talk about which part of the distribution you're trying to find the area for, it can be a little tricky. So beyond usually means sort of more extreme. So think about beyond as sort of going this way, the area beyond this way. So just like the area above is, so we talk about above and below, it's sort of different than larger, smaller portion, because regardless of where you are, the area below z is going to be to the left. Right? So the area that's more negative or more, is always going to be the left. The area above z is always going to be the right. So even if you're over here at -2, this is the area below, that is the area above. Right? So it's a little bit different than the larger, smaller portion, because depending on, as you go above 0 to positive z-scores, the larger portion is going to be the same thing as the area below. But if I go to negative z-scores, the area below now corresponds to the smaller portion, not the larger portion, because of where it is. So the language can mean slightly different things depending on what's being asked. Okay. So then you may be asking, well, what do we do about negative z's? Because if you look at the z table, and most z tables that get provided, they don't include negative z's. They just give you the areas for the positive z's, and that's it. The reason for that is because z tables are already fairly lengthy. Like there's usually a lot of pages and a lot of values for them, and the negative numbers just repeat the positive ones. So because a normal distribution is symmetric, if I find the area that corresponds to a positive z-score, it's going to be the same area for the corresponding negative z-score. So just like the area from the mean to +1 is 34%, the area from the mean to -1 is also 34%. So I don't necessarily need to repeat all the values for the negatives. I just need to think about what the area, what number I'm looking for and how to really compute the area, which is why it's important to keep in mind the sort of larger, smaller portion stuff, because if I look up the larger portion, if I want to know the area above -1, for instance, what's the area above a -1? Well, okay, that's going to be the larger portion relative to -1, which means when I look it up for 1, I still need to look up the larger portion, because the area above -1 is going to be the same as the area below +1. Both of them correspond to the larger portion of the distribution. So sometimes that's why it's really important to draw out what it is you're trying to do, so that when you go to figure out, do I want the larger, smaller portion and what it corresponds to, you won't get confused. And I'll show you some examples of that in just a second. So because the distribution is symmetric, areas above, between, and below positive z-scores are the same, or they're equal to the areas below, between, and above negative z-scores. So remember, there's no such thing as negative area. So if you're trying to compute the areas for problems related to the normal distribution and probability in the area under the curve, and you do something and you get a negative area value, something's wrong. You shouldn't. There's no such thing as that. You can't have negative area. So I'd rethink what happened and how you got to that negative point. So again, what about negatives, right? So just like, again, the area that was above 2.16 is the same thing as the area below negative 2.16. Right, the area above a negative 2.16 is the same thing as the area below a positive 2.16. The area from the mean to 1 was 0.3413, which means the area from the mean to negative 1 is also 0.3413. It's just sort of illustrating that because it's symmetric, the values that correspond to the positive scores also apply to the negatives, but they're sometimes flipped. So you gotta really draw the picture out and figure out what area you're really looking for to sort of keep that straight. So these are sort of tips. Keep in mind, or these are things to keep in mind. That the total area under the curve is 100%. So again, if you're looking for area of something, right? It doesn't matter, some problem, you're looking for area, and you compute an area that's more than 100%. Like, oh, the area is 110%. Something's wrong. You can't really have more than 100%. Unless you're sort of adding curves together or something. But it's just one normal distribution, 100% is going to be the maximum. The area above or below the mean is 50%. So if you're dealing with values that are on one side of the mean, you shouldn't get anything that's bigger than 50%, right? Because it's all on one side. So your number should make sense as you start to compute them. Think about, wait, does this number make sense? Does it seem too small? Does it seem too big? Relative to the rough estimation chart, relative to knowing that 100% of the area is under the curve, that 50% falls on both sides. Think about all those things and figure out, okay, does this number make sense? Does it seem like it's too big or too small for where it is in the distribution? Okay. So tips. These are the tips I was thinking of. Tips to remember. So before you do anything when solving some of these problems, you should always draw a picture first. Draw a normal distribution, put in the z-scores, put in the raw score, corresponding raw scores to the standard deviation, so you can actually get an idea of what it looks like, and then start to figure it out. So the percent of area above a negative or below a positive is the larger portion. Word. All right, so if I'm drawing this out, here's the positive side, here's the negative side. This says the percent of area above a negative or below a positive. So if I'm sitting here and above is the same thing as anything here and below. So the area above a negative or below a positive is the larger portion. And it's the flip side of that, actually I'll just draw it again, is the percent of area below a negative and above a positive are going to be the smaller. So here's my distribution again. Here's my negatives. Here's my positives. If I find any negative number, the area below that number, or any positive number, the area above that number is going to be the smaller portion. Right? Because for the pink, right, this is all large. For the green, this is all large. Okay. For here, the green is there, and for here, pink is here. So that's what those two things are saying. The area, the percent of area, or the area above a negative or below a positive z, is a larger portion up here. The area below a negative or above a positive is the smaller portion. Always draw a picture first before starting to figure this stuff out. Draw a picture. Can't say this enough. Always draw a picture first We're trying to figure out the areas. Percent of area between two positive or two negative z-scores is the difference between the two mean to z areas. Actually, it's really the difference between two of the same areas, but we'll just stick to mean to z. Percent of area between two positive or two negative z-scores is the difference between the two mean to z areas. What? Let's look at that. If I have a distribution and I have two positive numbers, I'm going to use a different color. I use pink, I guess. I have two positive numbers, whatever they are. This is a positive number, that's a positive number. And I want the area that's in between them. I can find that by using the area that is the mean to this number. All right, I can find this area between the two of them. And then I can also find the area from the mean to this number, this area. And then I can subtract those two, and what it's going to give me is the area that is in between the two positive numbers. All right, so read that again. Percent of area between two positive or two negative z-scores is the difference between the two mean to z areas. Find the mean to z for each value and subtract the two. Make sure you take the larger minus the smaller area so you don't get a negative area. And it'll tell you the proportion or percentage underneath the curve between the two of them. So in the same way, just to be complete here, if I have same or similar distribution and I want to look at two negative numbers, right, this one and say that one, it's a negative number and a negative number, and I want the area between the two of them, well, I can find the area from the mean to this one, right? Find this area, and the area from the mean to this one, find that area. And I can subtract those two areas, and what's going to give me is the area in between the two numbers I'm looking for. All right, so the percent of area between two positive or two negative z-scores is the difference of the two mean to z areas. All right, cool. Always draw a picture first. Most of the time, when I see students working on this stuff and they make mistakes, and they sort of, you can see where they sort of have gone wrong, it's likely they tried skipping the step where they're sort of trying to draw a picture and figure out how to solve it. And because they don't have that picture in their mind, it's easy to sort of make the wrong decisions and make mistakes. So take a second, just like I did, these don't take very long. Take a second, draw the picture out, figure out what area you're looking for, and then start to go to the Z table or go places you need to go to figure out the areas and work it out. But draw that picture, take that a couple seconds to do that. Converting and finding areas. So that table E10 that I was talking about gives areas under a standard normal curve. So like with the have need chart, if you have raw scores, convert them to Z's first. Draw a normal curve with both the z-scores and raw scores there, like we've talked about. Then find the areas using the z-scores that correspond to those raw scores. So convert first, draw the curve out, figure out where it needs to, where the areas are you're looking for, and then find the area using the z-scores or the z-table that's in table E10. All right, let's talk about some examples. So let's talk about an example applying all this stuff together. So here's my normal curve. Again, there are some lines there. They're kind of faint, but they're sort of to mark off where the standard deviations might be. So in a normal curve with a mean of 30, standard deviation of 5, what is the proportion of scores below 27? So the way that I would approach this, again, is to find, if I know the mean here is 30, standard deviation is 5, so that's 35. Oops, 30, 35. That's 40 is somewhere. I can't really see the lines very well. 40, and then over here is 45. So here's 25, 20, and 15 over there. Okay, something like that. So this also corresponds to 0, 1, 2, 3, -1, -2, -3. Okay, so there's all the corresponding pieces on the bottom there. And then what it's asking is, what's the proportion of scores below 27? So I don't know. I don't know exactly where 27 would be, but I know this is 25, 26, 27. It's going to be somewhere, you know, somewhere here. It doesn't have to be exact. So here's my 27. Okay, so that's where 27 is, somewhere in there. And I know it's saying what's the proportion of scores below 27. So all right, it means I want the area scores going this way. I want this area here. And because this number is below the mean, I don't know what z-score corresponds to it, but I know it's below the mean, which tells me that this area that I'm looking for, this area, whatever it is going to be from the smaller portion. Right? I'm going to need the smaller portion of the distribution because it's below the mean, and the area below negative numbers is the smaller portion of our z table. So again, given those steps we just talked about a second ago, the first thing is I need to convert. So I need to convert 27 to a z-score. So 27 minus 30 over 5 equals, it's going to give me a -3 over 5. 3 divided by 5 equals 0.6. So this means this is a -0.6. So don't forget to carry the negative over. I took 3 divided by 5. I got 0.6, and I almost forgot that's a -0.6. So that means that the z-score that corresponds to this this 27 is 0.6. All right, so the number I'm looking for really is this 0.6 is the z-score. Right, the 27 really is the raw score corresponds to it. Okay. So I'm looking for 0.6. Because I know it's really, it's really a -0.6, but when I go to my z table, it's only going to give me positive numbers. So I'm going to look up a positive 0.6, but I'm going to keep in mind, because I already figured out that I want the smaller portion, I'm going to look up a positive 0.6, look up the area for the smaller portion, and that's going to give me the area that I want. So let's look at that. So if I go to that z table, I go to my z table there, I need to find a z that corresponds to 0.6. All right, so it's not on this side, so okay, it's over here. So 0.5 down here, 0.6. Okay, so here's my z-score. It gives me my mean to z, larger portion, smaller portion. So like I just said, because of the way I drew this out, I know that what I want is the area that is relative to. Put it up a little bit so it's not writing on it. So here's my 0.6, and the smaller portion is this last column here. So 0.6 smaller portion is 0.2743. So the area I'm looking for is 0.2743. Okay. So it tells me that my area, this area that I'm looking for here, is about 27.43%, or you could leave it as 0.2743, or even say that it's roughly 27% or whatever. All right, all these things would be sort of acceptable answers for this. When asked what's the proportion, well, at least, okay, it says proportion of scores, so you should leave it as a proportion. So this really is probably the best answer, as that's the proportion of scores. If you got to this point, you actually gave me an answer 27.43. I wouldn't be like, well, you said it in percentage, so it's wrong. I'm going to get that you got that you've got the gist of how to find this, and that's what's important to me. Not that the answer is in the right format or something. This isn't Jeopardy. If if you don't answer in the form of a question, you don't get the answer or something. It's not like that. So a number curve, same thing, mean of 30, summation of 5. What is the proportion of scores that fall between 26 and 35? All right, so let's set this back up again. So we know that the mean is 30. Summation of 5 again, so I can't really see the line, so it's funny. So 35, 40, 45, or somewhere around here, somewhere, I don't know. I think it's corresponding. It's hard for me to see the lines. And then we got 25, 20, and then out here somewhere is 15 or something. Something like that. It doesn't have to be perfect, it just needs to be sort of close so you can get an idea. So between 26 and 25. All right, again, I don't know what these are exactly, but 26 is going to be somewhere near 25, so there's 26. Okay, so there's my 26 numbers there. And 35 is right at the standard deviation, so that's cool. So right away, when you see that, you know that this is the mean here, right? You should know that this is 34% roughly. I don't have to look anything up. I know it's 34% between the mean and z. So this is 1, 2, 3, -1, -2, -3. I already know that the area between 0 and 1 is 34%. So I don't need to look anything up. I know that if I'll do it anyway to show you, but I know this is going to be roughly 34%. So all I need to do is find, because this doesn't go all the way to 25, so it's going to be a little bit smaller. But in general, the area that I'm looking for, the area that I want, is the area between these two numbers. Those are the numbers. That's the area that I'm looking for between 25 and 35, 26 and 35. I mean. So let's convert. So 26 minus 30 over 5 equals, that's -4 over 5. And then we also need to figure out, just for the sake of argument, if you forgot this part, we could look, you would just do 35 minus 30 over 5 equals 5 over 5, which is 1. So -4 divided by 5. 4 divided by 5 gives me 0.8. So it's a negative, which I can't forget that. So I'm assuming a -0.8. That's my answer. So I can go here for a second and say, all right, well, let's keep that in mind. That down here on the z-score scale, I'm looking for a number that corresponds to -0.8. That's the number I'm looking for there, but I want a 1. Those are my two numbers that I'm interested in looking at the area between. Okay, so -0.8 and 1, so let's look at those on our z table. Let's just look at 1 real fast just to make it sort of easy, and then we'll come back to 0.8. So for 1, again, I'm looking up the mean z for both of these. Now, the reason I want to do that, if you can still see me here, with this distribution, right, I want the area that's from the mean to that z and the area from mean to that z. I want those areas. Maybe a little hard to see, and I'll show you when we come back to the slides. But so if I look at 1, the area for the mean to z is 0.3413. Okay, so that's good. I'm going to write that down so I don't forget, and we'll see it in a second. So for -0.8, the area is, oops, wrong one. For 1, the area is 0.3413. Okay. For 0.8, the area from the mean to -0.8 is the same thing as it is from the area to +0.8. So we're going to look up the mean to +0.8. And it looks like it is 0.2881. Let me write that down. This is 0.2881 is the areas. These are the areas. And that's it for the for the Z table. All right, and go back to our PowerPoint here. I got those two areas written down. So now I know those are my two areas. What do I do with them? Well, I want to know the area between the two of them. So if I find the area to here and the area to there, I can add them both together. So the total area is going to be 0.3413 plus 0.2881. Phone's being weird. 0.3413 plus 0.2881 equals 0.6294. 6294. All right, so that means that the area, this whole area from here to here, is 0.6294, which means that this, we can say this area here is roughly, I don't know, roughly equal to 63%. It's asking again in terms of proportion, so you could just simply leave it as the answer as 0.6294, and that's totally fine. Let's do another one. All right, let's say we have the Stanford-Binet intelligence test has a mean of 100, standard deviation of 15. So this gets a little tricky now. It's saying how many people out of 1,000 would have IQs between 120 and 140. Okay, so a couple things I would think about first is that, all right, since the mean is 100, both 120 and 140 are on the same side, the positive side of the mean. So they're both going to be related to positive z-scores. Okay, so that's good. So let's figure this out here. We can actually plot this out and say, okay, since the mean is 100, this actually is fairly, I think it's still fairly accurate. The Stanford-Binet has a mean of 100, standard deviation of 15. It's sort of designed to be that way. So I can put that the mean here is 100. Means this goes up to 115. This is 130. And somewhere up here, it's 145 or something. And then here, this is going to be, I'll look for the line here, 85, 70, 55, somewhere over here. Oops, not 50, 55. Like that. Okay, again, not perfect, close enough to sort of give us an idea. I also know that this corresponds to 0, that's 1, that's 2, that's 3, this is -1, -2, -3. Okay. So we can look at, all right, so it's saying what's between 120 and 140. All right, so again, I don't know exactly where it is, but it's going to be a little closer to here, I would imagine, than it is to there. So there's my, let's say this is my 120. I'll put it in a different color. So here's my 120 that I'm interested in. Okay. And then I'm going to go to 140, which is like way up here somewhere. And it's barely even noticeable. It's my 140. Okay. And I definitely want the area that is between, that's here somewhere, right? I want the area that's in between the two of these. So the way that I'm going to do that is I'm going to look at the mean to z value, which is here. Okay, here's my mean. What I'm going to find with these is I want to find the area that goes from the mean, goes from this mean to that mean. Okay, I'm going to find that area. And then I'm also going to find the area that goes from the mean to this score here, those two areas. And then once I have those two areas, I can take the larger area, subtract the smaller area, and what's going to be left is the area in between 120 and 140. So because they're on the same side of the mean, I can use the mean to z column. And again, you can use any column actually, but I'll just show you with the mean to z column. The area to each, subtract them, and what you're left with then is the area between them. So let's find the z-scores for both of them, and then we can find the areas and show you how it works. So first, 120. So 120 minus 100 over 15 equals 20 over 15. So 20 over 15 gives us a z-score of 1.333. So for 120, or I should say the z for 120, the z for 120 equals 1.333. Okay. The z for 140 equals same process, 140 minus 100 over 15, which is 40 over 15. I'm pretty sure it's like 2.666. 40 divided by 15 equals 2.667. So the z for 140 equals 2.667. So I have this z-score and that z-score. Let's look at the areas to each one. So what's the area corresponding to that one, the area corresponding to that one, and we're going to stick to the same column. Again, as long as you use the larger portion for both, the smaller portion for both, or the mean to z for both, you'll get the same. It's the same process. It doesn't make a difference, but I'm just going to show you using the mean to z, just because I seem to like that one better. So I need to find corresponding to 1.333. So I'm not going to be able to find 1.333, but I can find 1.33. It only goes to 2 decimals. 1.33. The area from the mean to z is 0.4082. 0.4082. And you'll see that clear in a second when I go back to this slide. 0.4082. For 2.67, which is here, 2.67, you get 0.4962. 0.4962. All right, awesome. Let's go back to the slide so we can see it a little clearer. All you need to do now is subtract them. Keep in mind, whichever one is the larger area, take that one and subtract the smaller area from it. So the area that we want, which is the area between 120 and 140, right, that area equals 0.4962 minus 0.4082. Subtract those two like that. 0.4962 minus 0.4082 equals 0.088. Okay, so you think about this. So this tells me this is roughly, 9%. 9% of people fall in this range. But you get to this point, you get to the 9%, many of you will be tempted to stop there. You're going to be like, oh, that's it. I got a percentage, I'm done. Go back and read the original question. So it says, how many people out of 1,000, right? So you got to take 9% at 0.9 and multiply it by 1,000. 0.9 times 1,000 is, well, it's not 9%. Sorry, I just did it wrong. It's 0.09. 0.09 times 1,000. All right, so it's either going to be roughly, 88 people, you can say, because if you actually use this times 1,000, it's roughly either 88 people as the answer, right? Or if you had already sort of rounded it up, it'd be 90 people, somewhere in there. Okay, so we take 0.088 times 1,000. It moves the decimal over, and you get 88 people. So the answer is not the 8.8%, but roughly 88 people would have a score between 120 and 140 if you had a sample of 1,000 people. When the numbers are on the same side of the mean, so if you're looking at two raw scores or z-scores that are on the same side, so two positive z-scores or two negative z-scores, you can find the area by subtracting. Find the area to the larger number, the area to the smaller number, and subtract them, and it'll give you the area in between. All right, so when the scores are on the same side, you're going to subtract their areas. Same side, subtract. Say that like over and over again. It's like your mantra, right? Same side, subtract. Same side, subtract. So that when they're on the same side of the mean, you're going to subtract. Okay? Same side, subtract. Going back a few slides, I wanted to remember that here, back here, that when we looked at the areas for 40 and 60, they were on opposite sides of the mean, and we found the two of them and we added them. So when they're on opposite sides of the mean, like one negative z, one positive z, you're going to find the areas and add them. Opposite sides you add, opposite sides you add, opposite sides you add. Same side, you're going to subtract. All right, same side, subtract. Opposite side, add. Same side, subtract. Opposite side, add. Okay? So a way of sort of remembering, if you're looking at this and they're on the same side, you're going to find the areas to both, you're going to subtract them. If you're doing the areas for values on either side of the mean, or on opposite sides of the mean, you're going to find their two areas and you're going to add them together. Opposites add, same side, subtract. Let's do one last example, and we'll wrap up normal distribution for the day. I'll put this right at the end, I think, here too. Okay. So, last one. Same setup as before. We have a mean of 100, 115, 130, 145. I can't see the lines. 85 is like here. And then it's got to be like there's 70. And then 55 somewhere over here. Okay. And then this, of course, corresponds to 0. 1, 2, 3, negative 1, negative 2, negative 3. All right, there's all the values. Okay, so this one's a little bit different. What would you need to score to be higher than 90% of scores? So, let's maybe take a little interpretation. What would you need to score to be higher than 90% of scores? So what score would you need, another way of phrasing this, if you wanted 90% of scores below you? What score do you need to have for there to be 90% of the distribution below your score? So 90% is obviously a larger than 50% proportion. So we're talking about a larger proportion, somewhere around 90%. I know that if I start at 100, that this is 50%. I know that already, right? This is 50. 50% going to the mean. I know that up to that point, That's 50%. If I go from 50, if I go from the mean to 1 standard deviation, here, I go there, that gives me another 34%. So combined, this 50 plus 34 is a combined from all the way to the bottom. Right, if I look at the cumulative probability here, all the way from there to there is 84%. Right? It's 50 plus 34 all the way to that point. And that includes like all of this. Right? Everything, all of this includes all, you know, the about 84% of the distribution are included in here. All right, so this is all so far 84% up to 1 standard deviation. That I know. If I go to 2 standard deviations, I add another 14%, which is going to put me at 96. All right, no, 98. It's going to put me at 98% if I go all the way to there. Right, so to here is 98%. So it's too far. So wherever I'm going, whatever I'm looking for in terms of the area, again, I don't know what number it is, but it's got to be somewhere in between here, because whatever this number is, I need 90% of the distribution, right, to be all the way up to that point. So again, I don't know what the number is, but I do know that some value between the first and second standard deviation here is going to give me a percentage, a proportion that is going to be relatively close to 90%. So I don't know what it is yet, but I want it to be 90%. So that means I'm looking for a value in the Z table that is the larger portion. And obviously, 90% is a larger portion. But again, I don't know what this is. I don't know what number it is, but I know it's got to be somewhere between 115 and 130, because if I go to 115, it's only 84%, and 130 gets me to 98%, so it's got to be somewhere in between. So this is sort of a guess of what the area would look like. All right. So I'm going to start this process the opposite way. And I need to find in the larger portion column, right? So look, remember this is mean to Z, larger portion, smaller portion. In this larger portion column, I need to find a number that is close to 90%. All right, so here we got 0.8997, 0.9015. So you can think of this as, you can really, if on an exam you pick either one of these and use 1.28 or 1.29, it wouldn't matter to me. It'd be fine. You'd be close enough. If you like, if you're, you know, some kind of way of deciding which one to choose, I like to think of the sort of Price is Right rule, which is, you know, try to find the area that is closest to the area you want without going over. Okay, so 0.8997 is the closest to 90% without going over, because this actually is including a little bit too much. So 0.8997 is a slight underestimation. So the z-score I want is 1.28. But again, if you use 1.29, not a big deal. 1.28 is the closest, largest portion, closest to 90%. So 1.28 is then the z-score that I'm looking for. 1.28 is my z. Okay, great. But it says, what would you need to score on the IQ test? So what IQ do you need to have? Not your z-score, it wants to know what IQ. So I need to convert this over. Thinking about the have-need chart, I started with my table E10. I converted it to a z-score, so I did the first step. Now I need to convert the z-score back to a raw score. So to get my raw score, I'm going to take and use my z-score, 1.28, times my standard deviation, which is 15, plus my mean, which is 100. And if you put all that together, 1.28 times 15 equals 19.2 plus 100 equals. So that tells me that the score that I need to be better than 90% of IQ scorers is roughly 119.2. And that would be your answer. Okay, that wraps up normal distribution. And we're going to move from here to talking about how do we use what we know about the normal distribution to start testing hypotheses and stuff. So that'll move us into sampling distributions of the mean and how that relates back to normal distributions and probability and stuff in the next video.